So yes, let's talk about the last 2 years of my life, which is network telemetry. Here we break telemetry into two parts. Monitoring, where data is generated and exported, and centralized collection of this data. This is an active field and there's tons of papers on cool new monitoring techniques. And to get a holistic view, we need diverse telemetry, such as flow paths, packet latencies, losses, queue depths, and various packet counters. To achieve a network-wide view, we centrally collect telemetry reports, and the collector server aggregates the data which is used to get an insight into the network state. And we can then do network-wide optimizations using these measurements. And our work, it focuses on this arrow here. Here, we highlight the amount of processing required just to receive measurements as the network grows. And behind this figure is a state-of-the-art collector from NSTI 2019, and we plot two very different monitoring systems being collected. First, we have the red line, which is INT. And INT is kind of the poster child for fine-grained telemetry. It's incredibly powerful and can generate telemetry reports for every single packet in a network. And it's of course super costly, and to be reasonable, we sample less than 1% of traffic. On the opposite end, we have NetZero from SIGCOMM' 2020. And this system greatly reduces the load by only reporting detected telemetry events, specifically loss events in this case. So we lose insight, but reduce the collection load accordingly. However, this is still costly. So for example, look at the cost at 1,000 switches. We burn thousands of cores just for data aggregation. And this is such a waste, because these cores could do valuable work, say like running VMs or doing actual analysis. So we want to save the CPU while inserting a high rate of data into server memory. So why not use RDMA? This is what it's designed for. So RDMA is cool. It allows network cards to process memory operations directly without involving the underlying CPU. And it does this by directly making calls to the server DRAM, resulting in high performance operations and freed up CPU cycles. And it's so fast that a single network card can process more than 100 million write operations per second. So question is, can we get this to work for telemetry? So here we do not have a typical RDMA scenario where servers make remote memory operations, but we have switches that want to populate data structures. And this is what our work is doing, CPU bypassing telemetry ingestion. It can't be that tricky, right? Just implement RDMA support and you're done. Well, we were hoping so too when we started the project, but there are several issues here, and let me highlight just one of them. It is that RDMA requires explicit addressing. So when we generate a memory write request in RDMA, we also need to state at which exact address we want to write the payload. And we can't really do fancy if statements or chaining and hash tables, and this gets tricky. So let's take a very simple example. We want to populate a list with telemetry information. Just some data that we want the CPU to iterate over, say like real-time packet losses. And let's assume that the first switch knows that index 0 contains some data and therefore it should write into index 1. So it writes a report to memory. But what happens if two other switches want to write at pretty much the same time? So what should be at memory 2? Switches need to somehow synchronize this. Obvious solution, we could just allocate dedicated lists for each switch. And this is not a problem. Switches just track their own head pointers, so there should never be any race conditions here. But there are a few issues with this approach. First, it's inefficient. There will be load imbalances in the structures since switches fire reports at wildly different rates depending on what is going on. And some buffers could stand almost idle while others might quickly saturate. And we want the control plane to quickly react to events, and this approach requires iterating over allocated buffers to find which ones are reporting issues. And some hyperscales can contain thousands of switches, and this adds unnecessary delays to reactivity. So why don't we just coordinate a shared list between switches? And switches take turns, process shared index pointers, and stay in sync. But this is an issue. So telemetry is a constant stream of information, and we cannot simply pause reporting while we handle coordination. There's no stopping of data until it's our turn to report. And in-ASIC buffers are small, and switch local CPUs are easily overwhelmed. Additionally, this opposes overheads and complexities for inter-switch communication, which is not good given the limited resources in the switching hardware. So why not just locking? Let's make the operations atomic. A lock could be attached to each memory buffer, and switches check the lock and conditionally claim ownership. But again, same set of problems as before. We cannot simply pause the stream of telemetry, and locking this way prevents simultaneous in-flight reports, significantly reducing collection performance. And we still have to synchronize memory pointers. all of these solutions share one big problem. The RDMA protocol is complex, and implementing support in every telemetry-capable switch is a waste of resources just for this. So yeah, what I want to say here is that RDMA for telemetry is tricky. So we cannot just use RDMA as is, so let's take a step back. First, we want low overheads at switches. Their resources are limited and they have more important things to do than just telemetry. Second, we want coordination-free updates, keeping complexities low and performance high. Third, we do not want to rely on the CPU for data ingestion. This is the current performance bottleneck even after years of optimizations. And finally, let's not forget about what we're doing. Of course, we want the data to be queryable for analysis. A random block of garbled reports is not exactly useful. Then any collection benefits will be lost as soon as we have to query the information. So we need a lightweight protocol where switches blindly push telemetry reports without an inline CPU while still being organized and aggregated. So in a nutshell, we want memory layout aware RDMA verbs. So let's introduce our actual solution, Direct Telemetry Access or DTA. Switches generate telemetry reports with new headers, DTA headers, and these packets are sent towards a collector, just as usual, but instead of reaching the collector, they get intercepted by the last hop towards that server, by the top-of-rack switch that we here call the translator. And this translator top-of-rack, it translates DTA into RDMA, acting as the sole manager of populating the telemetry storing data structures at the adjacent collectors. In comes DTA and out goes RDMA packets. And these are then handled by the NIC, so the collector no longer has to care about data ingestion or aggregation. It just hosts the data structures and performs pure data analysis. So the switch reports some measurements. The translator processes this information and figures out how best to aggregate this information together with all other previous telemetry reports it's received. It generates RDMA operations to write this into collector's memory, and the collector magically then knows about the new measurements. And this design manages to fulfill all of our requirements. So first, we designed the DTA protocol to be very lightweight, containing just the essentials to inform the translator about metadata regarding a telemetry report. Second, switches don't need any collaboration. They just fire and forget a report and the translator handles aggregation. Third, we entirely bypass the CPU by supporting legacy RDMA. And finally, DTA achieves efficient queryable aggregation by the translator having sole ownership over the data structures. And thanks to this, we can expand on RDMA with new telemetry verbs. And we have designed 4 new telemetry-capable verbs for RDMA using this technique. So first, we have key write, allowing basic key value storage of data. Then there's postcarding, which is for aggregated key value storage that's a bit more complex, but very powerful for some workloads. We have append, some of the problems of chronological storage. This one is guaranteed to be collaboration free. And finally, we have key increment to store network-wide counters. And together, they achieve a broad support of monitoring techniques proposed by the community. And let's zoom into one of them just to get a feel for what's happening. So let's collect network path through DTA. First, a switch reports a network path for a flow. This report reaches the translator that will populate a key value store of flow paths. The flow identifier is stated in the DTA headers, and this is then hashed into 2 memory locations on the underlying server. And we now have the path stored and queryable with redundancies in the key value store. Then another path is reported for another flow. Again, we know the flow ID and we hash in the 2 memory locations where we store the path, and look at that, a hash collision. So indeed, this is probabilistic storage. However, through checksumming and consensus voting, we can with high certainty detect collisions at query time. And our experiments show that just 30 gigabytes of storage is enough to allow a greater than 99.9% query success rate when storing 10 million flow pods. So it is probabilistic, but still highly reliable. So wrapping up, DTA is generic. It's not designed with a specific system in mind, but allows broad support of different monitoring systems. And DTA is lightweight. Recall how switching resources are very valuable. Turns out that DTA is almost as lightweight to generate as traditional UDP. So for most of the switches in the network, DTA is basically free. And it's ridiculously fast. DTA achieves an order of magnitude performance improvement compared to CPU-based collectors. And this is while simultaneously freeing up the CPU cores to do other work at the collectors. We have released DTA as open source together with some guides on how to set up the system to build upon or integrate with new monitoring systems.